Welcome to AI for Specialists. So, artificial intelligence, it's really transformed industry, hasn't it? Promising all this incredible efficiency, but integrating it into physical systems, factories, power plants, that's created a whole new kind of threat, a really critical one. Physical adversarial AI attacks.
Exactly. And that's really what we want to get into today. Our mission, if you like, is to deconstruct how these inherent AI vulnerabilities, they're now showing up as actual tangible physical security risks.
Real world stuff.
Real world stuff. Evaluating, the potential for actual industrial sabotage and maybe outlining some multi-layered defense strategies.
Okay, so let's start there. This whole idea of adversarial AI. Initially, it was more like digital glitches, or tiny changes to a picture. Maybe you can't even see them, but they make a sophisticated AI. I think a panda is a gibbon or something. Wild, but like you said, digital.
But the interesting thing, the fascinating part, is how that limitation kind of forced a change. Those early, purely digital attacks, they often just, fizzled out in the real world.
Why was that?
Things like camera noise, different lighting conditions.
Yeah.
It created what people call the digital to physical gap. And this gap, it pushed attackers to become, engineers of deception.
Engineers of deception, I like that.
Yeah, creating what we now call physical adversarial examples, or PAEs. These are actual tangible objects or, modifications to the environment, specifically designed to fool AI robustly right there in the physical world.
But I thought AI was meant to be robust. Why is it so fragile, so easily fooled by these optical illusions, as you put it?
Well, it's because AI doesn't learn like humans do. It learns these incredibly complex statistical patterns, but also shortcut features. It doesn't get the underlying meaning, the semantics.
Okay.
And we've seen some pretty startling examples. These aren't theoretical. They're demonstrated vulnerabilities, like strategically placing stickers on a road surface. That could potentially make a self-driving car just veer into the wrong lane. Or, another one, just some black and white tape on a stop sign. To us, it looks maybe like graffiti, right? But it caused a real vision system to misclassify it as a speed limit 45 sign.
That's genuinely unsettling. And the hidden risk here, the really tricky part, is that these systems can pass millions of standard tests, look perfectly fine.
Absolutely.
But still have these latent vulnerabilities, these hidden blind spots, where an adversarial input just triggers a complete misinterpretation. Catastrophic, potentially.
And if you connect that dot to the bigger picture, AI is now deeply embedded in operational technology, OT. The control systems running factories, power grids, transportation networks.
Right, the critical stuff.
Exactly. So an adversarial attack isn't just about stealing data anymore. It's a potential physical event. It could actually lead to industrial sabotage.
So can you give us some examples? What kind of physical attacks are we talking about?
Sure. Think about the visual domain first. You could have, say, 3D printed objects, maybe a little plastic turtle, but its texture or shape is designed so that an AI consistently sees it as a rifle from almost any angle.
Okay, that's weird.
Or wearable patterns. Put a specific pattern on a t-shirt, and suddenly you might become effectively invisible to AI systems designed to detect people.
Invisible.
Invisible to the AI, yeah. Then you've got the LiDAR domain, the laser sensors used in autonomous vehicles, robotics.
Right.
There are attacks called physical removal attacks, PRAs. They can actually exploit the sensor's firmware to make real objects, like a stack of shelves for a warehouse robot, or even a person just vanish from the AI's perception.
Oh.
By spoofing fake high-intensity laser points that trick the system into thinking the real object isn't there. And don't forget sound, the acoustic domain. You can craft audio signals with hidden commands embedded in them. Using techniques like psychoacoustic masking, they can be basically imperceptible to human ears.
But machines hear them.
But an automated speech recognition system picks them up clear as day. So, think about the stakes here. A successful attack could mean widespread blackouts, millions, maybe billions in damaged equipment, direct threats to human safety.
It feels different from something like Stuxnet.
It is different. Stuxnet, which was, over a decade ago now, that directly manipulated the control logic of industrial systems. These modern AML, adversarial machine learning, attacks, they target the AI's perception of reality, what it thinks is happening.
Which gives the attacker Deniability.
A much higher degree of deniability, exactly. A failure can just look like an AI glitch or maybe a sensor malfunction. Plausible deniability.
And it gets even more insidious, doesn't it, thinking about attacking the design files themselves?
Well, absolutely. Targeting things like CAD files or the G-code used for 3D printing, you could inject tiny, almost undetectable defects into the design of a critical component.
Like a jet engine turbine blade.
Precisely. Something that seems perfectly fine during manufacturing and inspection, but then fails catastrophically out in the field maybe months or years later, and it just looks like, material fatigue.
Okay, this is serious stuff. So, defenses. Is there a silver bullet?
Unfortunately, no. There's no single silver bullet defense. Building resilience here really requires a multi-layered approach, defense in depth.
So things like adversarial training.
Yeah.
Making the model itself tougher?
That's part of it, yeah. Model-level hardening, like adversarial training, is one layer, but it often comes with trade-offs.
Okay. Like what?
Well, sometimes it can reduce the model's performance on normal, clean data. Or a defense might only work against very specific types of attacks it was trained on. It's not a catch-all.
So you need more.
You definitely need more. System-level mitigations are crucial. Things like input filtering, maybe slightly blurring images to smooth out tiny adversarial perturbations, or using techniques called patch-agnostic defenses, PADs, which try to spot statistical anomalies that indicate an adversarial pattern and then sort of mask it out.
Right, but then you mentioned sensor fusion earlier, combining data from different sensors. That sounds like a good defense, no?
It can be, yes. Against simpler, naive attacks, combining data from, say, a camera and LiDAR can definitely help. But it also creates what some call the sensor fusion paradox.
Paradox. How so?
Because while it defends against some attacks, it actually opens up new, potentially more sophisticated attack surfaces. The fusion logic itself can be tricked.
Okay, give me an example.
So there's something called the frustum attack. An attacker could spoof fake LiDAR points. Now, these points are fake, but they're carefully crafted to be geometrically consistent with what the camera is seeing.
So they look plausible together.
Exactly. They align within the camera's view, frustum. So the fusion logic thinks, okay, camera sees something here, LiDAR confirms points there, must be real, even though it's entirely fabricated. It creates a convincing but totally false perception for the AI.
Tricky. So for the operators out there, the people running these systems, what are the key takeaways? What should they be doing?
Okay, crucial recommendations. First, adopt a secure by design mindset right from the very start of any AI project. Don't bolt security on later.
Makes sense.
Second, demand supply chain transparency. You need to know what's inside the AI systems you're buying. Push for an AI bill of materials, an AI BOM from your vendors, like a list of ingredients.
Right, know what you're getting.
Know what you're getting. Third, implement layered security model hardening, input checks, system monitoring, the works, and maybe most importantly, monitor the physical context, not just the pixels or the data points.
What do you mean by that?
Well, if your AI vision system says a storage tank is empty, but a completely separate traditional pressure sensor says it's full, the overall system needs to recognize that discrepancy, flag it, and probably revert to a predefined safe state rather than trusting the potentially compromised AI. Context is key.
So bringing it all together, it feels like we're entering a new era where the security of our physical world depends more and more on whether AI's perception of that world is accurate. And the scary part is failures might just look like random glitches, not deliberate sabotage.
It absolutely changes the defensive paradigm we need to adopt. We have to assume perception can be attacked.
It certainly gives you a lot to think about. Well, that's all the time we have today. Until next time on AI for Specialists.